Welcome to Calculus.
Our stress tolerance level has risen so high that nothing phases us.
On this episode, Stevenson will demonstrate
Let's talk about extreme values. Like extreme values, something intense. We can look at a picture and figure out extreme values. Let's practice that. We're good at that. So here's a function f of x. I know it's pretty. I gave you a whole bunch of points. Okay, they all have their own names and labels. Now, I have a question. Which of these points would you consider an absolute maximum? Which would you consider an absolute minimum on this closed interval from a to g? Don't think too hard. I know, this is a tough question. The absolute maximum would occur all the way up here at g, and the absolute minimum would occur all the way down here at a. Not too bad. Now here's another question. What if the interval changed? Instead of going from a to g, that closed interval, what if it was the closed interval from c to e? So I drew little lines there for you to illustrate it. Now, which point would be considered an absolute max and which would be considered absolute minimum? Hopefully you recognize the absolute maximum would be this top point up here, which would be D, and the absolute minimum would be down here, which would be C. Okay, so hopefully we're able to identify absolute extrema. So continuing this idea about extrema, we have to make sure we know how to talk about it, okay? Because there's two ways in which you can approach extrema. You can ask yourself, when is it happening, or what is it? So let's look at the following example here. So suppose I have an input of h, right here, and the output is f of h, so my function evaluated at h. So when the extrema happens, or where it's happening, is the x-coordinate. So if the question says, hey, when does this function have an extreme value? Then you know you're going to answer with an x-coordinate. Or if it says, where does it have an extreme value? You know you're going to answer with the x-coordinates, okay? Now, if it's asking what is the extrema, then that's the y-coordinate, that's the output. So it might say, what is the absolute maximum of your function f of x? Then you know your answer is a y-coordinate. So what is absolute extrema? So you have this definition in your notes somewhere. I'm just going to really quickly break this down because the way this is written can be a little confusing. So it says let f be a function with domain D where f of c, or then f of c is, and then there's two ways to define it. F of c just represents some particular input, and what is the output? So f of c specifically is the output of whatever this input is. Now what's the input? Well, they're describing it for you in two ways. It's considered the absolute maximum if the f of x, which represents all the other outputs, all the other y values on the graph, is less than this particular input, whatever it may be, which in this case, if it's an absolute max, it would represent the largest. If all the other outputs, again, are greater than this particular input, well then that particular input, or excuse me, that output, that y value, is representative or considered the absolute minimum. So that's what this is basically saying. So a little bit of vocabulary here. Global or absolute extrema, it means the same thing. So some textbooks call it global extrema and some will call it absolute. It's just really preferenced by the textbook and or potentially your teacher. So let's look at this instance now. Same idea, very similar function. This is called g, but notice the endpoints are open. So I gave you the same set of points. But which of these would you now consider an absolute maximum and which would you consider an absolute minimum on the open interval from a to g? Don't think too hard. Don't second guess yourself. Now, did you notice this actually has no absolute maximum or minimum? Let's look at this endpoint here. You can actually get infinitely close to it, but you can always think of a value higher. So if you might say, oh, so let's say this is 4, right? You could say, oh, it's going to be 3.9. Well, then I'll say, well, what about 3.99? And then someone else will say, what about 3.99? And then like Leo might be like, yeah, but what if it was like 3.9999? And then Chelsea's gonna be like, no, I got you. It's 3.9999999. You get the idea? It can just keep going. Same thing happens down here on the absolute minimum. You can think of a value to get close to it, but there's always another value that can be actually closer. So you can get infinitely close to this value here, but never actually equal it. So this thing has no absolute extrema. What if I change the interval to c to e? So here's the dotted lines. Now they're dashed because the interval is open. Since the interval's open, let's reconsider our position here. Which of these points do you think on this interval in the middle here could be an absolute max or an absolute minimum? Now this is an absolute maximum. On this interval here, at point D, we will have an absolute maximum. However, there is no absolute minimum, because although it's very tempting to say C down here is the absolute minimum, the interval is open. So again, we run into the same problem going, well, I can get infinitely close to it, but there's always going to be another value that's smaller to it, but I can't actually equal that value at C. Now that we've kind of gone through both these functions, f and g, let's look at them side by side. Let's remember, f of x had both an absolute maximum and an absolute minimum, but g of x didn't. Remember on the whole entire interval from a to, what was it, a to g, I think? Okay, whatever that whole interval was. Why was that? Why did f of x have absolute extrema but g of x didn't? Well, this is where the extreme value theorem comes into play. If your function is continuous on a closed interval, then you are guaranteed both a maximum and a minimum value. So look back at your notes. If you look at f of x was continuous on a closed interval. But g of x, it was continuous, but it wasn't on a closed interval. Extreme value theorem is an awesome theorem. It's our second existence theorem that we need to know. We abbreviate it as EVT. And basically what it says is if your function is continuous on a closed interval, you are guaranteed both a maximum and a minimum value. So here are some examples of maximums and minimums on closed intervals. So these are in your book. You can go ahead and add them in if you want. I'm a big proponent of visuals to go with it. But what this is showing you is how your maximum and minimums can exist at the endpoints at what's called an interior point. So essentially an interior point is any point between your endpoints. And it can be combinations. So you could have one extrema, one absolute extrema at an endpoint and the other one's at an interior point. So these are just examples that you can have of the different types of extremas.